So good morning and welcome to the part B of lecture 8. We will try to finish this lecture today, and the first subject that we shall discuss is that of an electric dipole and flux lines. And we said that an electric dipole is formed when 2 point charges of equal magnitude but opposite sign are separated by a small distance. So here we consider a dipole as seen in this figure 420, and in this figure we have point charges Q plus and Q minus, and we want to observe the electric field due to this dipole at this point P. So the first thing that we need to observe are the dimensions that make up the dipole, and the first one is the D, that shows the distance between the 2 point charges, Q plus and Q minus, and from the dipole, from the center of the dipole, we have the position vector R, and from the positive point charge, we have the position vector R1, and from the negative point charge Q minus, we have the position vector R2. So one of the most important point to understand with this figure is the distance R1, R2, and R, and how they related to the distance between the 2 point charges, making the dipole the D. And there are some approximations that we adopt, and we say that for those approximations to be viable, we say that the distance R, the one that we observed from the center of the dipole to point P, or the point of observation, must be far much bigger than the distance that is making the dipole, or the length of the dipole, or the length between the 2 point charges. And for that reason, we make an approximation that says that the difference between the two position vectors R1 and R2 should be approximately equal to d cos theta. And here I have made some simple approach in which you can see how that is possible. To start with, consider that this small triangle is a right angled triangle that takes the shape similar to that. So this from this point to this point, this is from the point where we have Q plus, and this is where the center of the dipole, and the other half is going to be where we have Q minus. So if you consider that to be your dimension, and we know the length of the dipole is D, then this is going to be a half D. And if you consider this to be a right angled triangle, that means we can be able to evaluate the length between R1. R1 is the one that is extending from that point, and the R is the one that is extending from the center, and the other R is extending from the other end of Q, or Q minus. Therefore, what we can do at this point is simply say, what is cos theta? Cos theta is considered to be this half, or this length, or the adjacent of this right angled triangle, and we can call it we can actually call it D1, and therefore you're going to see that cos of theta is going to be the adjacent, which is D1 divided by the hypotenuse, which is d over 2, and therefore the length of d1 simply becomes this value. Just taking this on this side, d over 2 multiplied by d over 2, and this cancels that. We have the length of d1, and that is half the length or half the distance, or rather r1 minus r, or vice versa. Actually, is actually r minus r1, because r is bigger than r1, and therefore the distance or the difference in the distance between r and r1 is going to be equals to d1, the one we have denoted as d1, and therefore that is the one that we have found out to be equals to this value. So if we approximate the length of d2, the distance between the center of our dipole and the of course along this R2. So this distance is the one that we are going to be calling D2. And if we follow the same analogy, we are going to say that cos of theta is going to be D2 divided by hypotenuse, which again is going to be D over 2, and then you're going to find that D over 2 multiplied by on both sides cancels out, and then we can see that D1 is going to be approximately to be D2, and therefore what we need is the total distance between R1 and R2. Of course, we know R2 is bigger than R1, and therefore it's going to be twice this distance that we have found out. So if you multiply this equation by 2, you are going to find that you have D1 plus D2, and this gives you D cos theta, and therefore this gives us our approximation for the two position vectors. Now, to evaluate the potential at this point, we know the formula that gives us the potential is, as we found out, is going to be inversely proportional to the r being the position vector. And of course, we said that contrary to how we evaluate E, we said E is always a factor of 1 over r squared, but from our last lecture we found that EV is a function of 1 over r, and for that reason, therefore, because one of them is positive, the other one is negative, that's why we are having the V due to Q1 being positive and V due to Q minus being negative. Of course, the only negative is coming due to the negative charge here, and therefore that reason we add them, or we have this subtraction arising due to the negative charge that is, or the opposite charge between the two charges, and therefore we just say that V is going to be evaluated as seen by equation 477, and if you evaluate this, you actually get this expression. Of course, that is quite straightforward. But then, since what we are interested in is this factor that we have evaluated here, that we have said is equals to d cos theta, and therefore when we replace r2 minus r1 with that function, we are able to generate this equation 478. And since we have said R1 is approximately equals to, of course, we have made this assumption here that the square of R is approximately equals to R1 and R2, because the average you actually of these two can give you this R. Therefore, that reason we we are able to develop equation 478. And from our knowledge of vectors, we know that this to be true, that any two vectors separated by an angle theta can always, if you say this is your D and this is your AR, the unit vector, then you can say that D cos theta is always equals to D, the vector, dot AR, the unit vector. So I think nothing is much strange there, and that can be said. And we can express our D vector as a scalar and its unit vector. If you remember that D is considered to be pointing or in the direction of Z, therefore that's why we adopt this AZ, and therefore we can actually come up with a new term that we are calling from this equation. We can adopt this QD and we call it a dipole moment. Dipole moment, and the dipole moment we denote it as P, a P being a vector, and for that reason we are able to characterize the potential V as a function of dipole moment P, and this P is pointed away from the negative charge towards the positive charge. And we also observe that if the dipole center is not placed at the origin, then we will have a different, we'll have the R prime indicating the position vector of the origin. No, previously we have considered the R prime being placed at the center at the origin, and therefore it had value 0 or 0 0. But if it is now not placed at the origin, we are going to be subtracting it at this point, and this is going, if you remember what we did with the AR, we said that AR hat is always equals to the vector itself, and in this case we're saying it's going to be equal to R minus R prime divided by R minus R prime modulus. Let me do some cleaning. And therefore, if this is our R, which is normally a vector or the distance, the unit distance vector that can be expressed as this, therefore, what this means for us is that this equation, which again we said can be expressed as R minus R prime modulus squared, therefore is going to be multiplied. It is going to be to add to this denominator. Therefore, when you multiply by R minus R prime squared, this term becomes R minus R prime modulus cubed. And that is why you can see this term taking that form, and therefore this now is representing the direction or the unit vector direction, which is R minus R prime. The next step that we need to do is to evaluate the electric field due to the dipole, as we have seen for the one that has the center at the origin. At the origin, the one that we have shown in figure 420 above. So we want to evaluate the electric field. What we have already done is to evaluate the potential at the point P. And now what we want to evaluate is the electric field strength at the same point P. And from equation 476, which was stated as this one, we said that the electric field strength is equals to the negative gradient of potential V. And since we have been given V, or we have evaluated V from above, we have said is equals to Q over 4 pi epsilon naught 1 over R1 minus 1 over R2 and this gave us QD cos theta over R squared Q over 4 pi epsilon naught. Of course, we did this evaluation. So from equation 476, and since we have been given V, we can always be able to express the gradient of V in spherical coordinates, as you can see in this equation right here. And what we can see clearly is that this equation 478 is only a function of theta and of R as far as the spherical coordinates are concerned. You can see that we do not have anywhere the factor phi is factored. And for that reason, we are going to lose the a phi factor, and that term goes to 0. So when we perform this differentiation or partial derivatives, the first one with respect to R and the second one with respect to theta, what we are able to do that to obtain this expression as expressed here. So of course we can see that the derivation, or when you differentiate V with respect to R, R is our subject. R is our subject here, and you know that that gives us, when you differentiate this, it is like saying d dr of r to power minus 3, and what that does to us is that my apologies, this is the result of what we have already differentiated. So we are first of all writing down our V, and we have said that V is equals to Q over 4 pi epsilon naught D cos theta all over R squared. And therefore, if you differentiate V with respect to R, it's equivalent to saying a constant, then d dr 1 or r to the power minus 2, and this derivative becomes negative k negative 2k. Of course, this 2 comes here, and then you minus 1, it becomes r to the power minus 3, and this is equivalent to saying minus 2k all over r cubed. K is the term that was not part of derivative, and therefore, if you remember, we had a negative here. That is how we are introducing this constant k. Then that will have a negative, the two negatives cancel, and we are left with r squared r cubed at the denominator. I guess here is not accurate. Or rather, I pressed k r twice, so this is supposed to become r cubed, and the other term remains as a constant. And you do the same thing for this other term that you are differentiating with respect to cos theta. We know when you differentiate cos theta with respect to theta, it gives you negative sine of theta. And if you also remember that when you are finding the gradient, we normally introduce 1 over r, and therefore this gives us r cubed at the bottom, and this becomes sine theta. And again, we had a negative, and the negative we had earlier, they cancel out, and we end up with that. So that is how we are obtaining this equation right there. And as you can see, we can factor out QD here, and QD we said is equals to P, the dipole moment. We can factor it out, and when you factor it out, we are going to be left with an expression that takes this form, as you can see the one that is labeled 482. And so as we conclude, we need to make some observations here that says that we note that a point charge is a monopole and its electric field varies inversely as R squared, while its potential varies inversely as R. That is something I've always said earlier, that E varies as 1 over R squared for point charge, whereas the V varies as 1 over R again for point charge. And similarly, we are now seeing that from question 480 and 482, we notice that electric field due to a dipole varies as 1 over 3. So that is a very important realization. This is for a point charge. This is point charge, which is a monopole, and therefore we are making another very unique observation that E varies as 1 over R cubed for a dipole, and V varies as 1 over R squared again for a dipole. So in similar manner, we can make conclusions in regard to higher order multiples, such as quadrupole, that is consisting of 2 dipoles, or an octupole that is consisting of 2 quadrupoles, and say that the E varies inversely as R to power 4, R to power 5, R to power 6, while their corresponding potentials vary inversely as R to power 3, R to power 4, and R to power 5, respectively. The only thing that we are observing here is that the potential has one lower power than the electric field. And the idea of electric flux lines, or as electric lines of force, as they are sometimes called, was introduced by a gentleman called Michael Faraday that lives during this period in his investigation as a way of visualizing electric field.